All right, we're back where we left off from pre-flight 6-1. Calculate the current through resistor 1. Yikes, that could take all day, it seems like, until you look at one of your loops. Choose this loop, it's pretty easy. I get a plus 10 here. What do you have to have as soon as you cross this when you go back to 0? That has to be a minus 10. So if I had a boost in 10, according to Kirchoff, I have a drop in 10 because that's the only resistor I have. So if I have a drop in 10 volts across 10 ohms, what's the current? It's 1 ohm. That's 10 divided by 10. So it actually, this is an example of a multiple choice question you're likely to see if you had the normal test, or it might be a question they could end up asking, which you don't have to go into great detail. You just notice you have one item each. So whatever the plus here is, that has to be the minus here. That's the nice thing about Kirchoff law. It allows you to not even have to look at some other things to solve some problems. So this is your loop. You got your plus 10, and you got your, this has to be a minus 10. And since you know what the resistance is, you solve it out for the 1 amp pretty easily. Okay? So what would change if you had a switch here and you opened it? 3 seconds. Well, how does that change this loop? If you put a switch here and you open it, how does that change this loop? And the answer is, it doesn't. So once again, that's the nice thing about Kirchoff's law. It allows you to focus on what's important here. Kind of like the Gauss's law helps us to find fields more easily. It helps you to focus on what charge you need to count to use to find what the field is. The Kirchoff law is a tool to use to focus on really what you have to know. And you looking at this loop, it doesn't matter what's happening on the inside because we have the same thing happen on that loop. Alrighty, so now what's the current through resistor 2? This could be a little trickier because I could pick a this way, I could pick a this way, or I could pick a this way, or I could pick a this way. And it doesn't matter which one you choose, but you have to choose one. So keep in mind, if I choose this path, now does that mean the current here is the same as the current here? I have 2 resistors. Not necessarily, because there's a break, there's a fork in the road there. And so I want to use something with 1 resistor. Is going to be a lot easier for me. So if I use just 1 resistor, it looks like the author has chosen this direction right here to use. Okay, by looking at the arrows. So now if I do a plus 10, well, now I got a minus 5. And I got a minus 5 over here, and that's a 10 ohm resistor. So if I'm now at 5 volts, I know this is 0 volts, so I have to have a 5 volt drop across this because I'm going to hit 0 back over here. So it's 5 volts and 10 ohms, that means it is a half an amp. So once again, if you choose the right loop, it can make the problem a whole lot easier. If I chose the top, I can do the top loop. It gets a little more complicated because I can have more than 1 current there, but I have only 1 source. So by choosing the loop with the 1 resistor, and I know what the potentials are, it actually made the problem a lot easier. Okay, so how do you know the direction? Well, once again, it doesn't matter. You can choose the wrong direction of things. Because you notice the author just chose this loop right here, and it came up positive, meaning this actual direction was the wrong direction first chosen. It's not a big problem, because now if you want to work it from the other direction, if you want to change the direction that the loop goes, then that means you're just gonna change how you work this current. You'd go this way. So plus 5 minus 10, now you add a minus 5. It all works the exact same way. And you'd find out when you solve for that current going through there, you get a negative 0.5, meaning you just had the opposite direction the first time. Okay? So it doesn't matter if you choose the wrong direction, you end up getting a negative current, means the current's going backwards through that one spot. All right, let's talk about some junction rule stuff. So whatever current enters has to leave. So in this case, I got I1 and I2. Well, if I1 coming in, it splits into I3 and I2. So in this case, I1 equals I3 plus I2. In that case. So now we're going back to here and we have some different things. So calculate the current through battery. It's not really telling you which battery, and there's two of them. Oh, it's this one. It says IB. So they're talking about this battery there, how much current is going through there. Remember, we just found this to be 1 amp, and we found this to be a 0.5 amp, but going what direction? Well, that was this direction, if you remember. So the author chose this direction for the current to go, and since the first time we ran this, we didn't run it back, we tried it backwards, but since the author said the current's going this way backwards through the battery, we actually found a positive 0.5 amp. So if I have a 0.5 amp hitting here, 1 amp hitting here, how much is hitting right here into the battery? Well, it's 1.5. Okay? So this was the 1 amp, this was the 0.5 amp going in this direction, opposite of that battery, because this is 10 volts, higher potential than that, going that way. Alrighty. So you choose your currents, you make whatever your equation is, you determine how you want to split that up. Whether this is I1 equals I2 plus this could call it an I3 or a 5 or however you want to call that. You don't have to do the number two. I know they keep saying you can do that, but I don't really see the need in that. Choose your loop in your direction, write down your voltage drops. Okay? And of course, then you write down your junction rule. Okay? So you're going to do these and this together to solve for what the current is. Alrighty, so slightly more simple diagram than what we just looked at. In the circuit below, we're given all of these things. Okay, getting that out of the way a little bit. So you label all your currents. You decide where you want your loops to be. Okay, so when you say you label your currents, I would actually tend to choose my loops first from this. Okay, I don't do the positive and negative. You can if you like. Okay, choose your loop direction. So I tend to label my currents after I've done my loops. It doesn't matter if I'm wrong. We'll find out. You just get a negative answer. So knowing what these are help me choose what my loops are. I could use this as one loop. I could use this as another loop. I could use this whole thing as another loop. So I have 3 choices for loops there. Okay, I love choices. So there's one loop. Then you would write down your equation for that loop. Okay, so in this equation is the plus, the minus, and then the other minus. But you notice they're not necessarily the same currents anymore. Even though you'd say, hey, that's a series. Well, we have a junction here. The currents do not necessarily have to be the same. So I've labeled this as an I2, and this is an I1. Okay, so you need another loop. There's loop number 2. So do the equation for your conservation of energy for your loop 2. You got your plus. I still got my I1. I'm skipping that. Now I have my I3. I labeled that. So it looks like my I1 plus my I2 equals I3. But I've drawn my loop this way. So there's my plus. There's a minus. There's a minus. And since I'm going backwards, that's going to be a minus on the E2. Okay? Then finally, I got to do my junction equation. Okay, so do my junction equation. So what I said earlier, my I1 and my I2, according to the directions of that this is showing, that the author chose that to be the current. I don't know that I would necessarily do it that direction, but if you're wrong, you just find that that would be a negative. Okay, so that was in the labeling all the currents. Like I said, it doesn't matter if you get the stuff wrong. It'll just give you a negative answer showing it's going the opposite direction. So I got my 3 equations. Okay, the rest is just math. Okay, so if you know your resistances and your potentials, everything else is just math and solving for your unknown. So I have 3 equations, but I have 3 unknowns in this thing. So I have 3 different currents. I don't know what any of these are. I have no idea what those are. That's why I have 3 equations to systematically go back and solve for which is which, or adding those equations together. Okay, so starting something a little easier. What is the correct expression for loop 3 in the circuit below? Okay, common question you might see on an AP exam multiple choice question. So this is your loop for loop 3. So you start with your E2. Then you're going to drop across this one, you're going to drop across that one, and then drop across this one. Okay, so which one of those would that be? Well, in this case, the E2, So the reason in this scenario with this picture that this is a actual plus, not a minus, is because we're going opposite of the current. That's why the author chose to do the pluses and the minuses on here, to see that you're actually going in the same direction. So technically that's going to be a plus. Okay? But if I'm looking at the directions chosen and I chose this to loop, I already know it's going to be the opposite. So I knew to change it to a plus. And then this is also opposite of the direction of the current, and that's why that was a plus there. Okay? May sound crazy, but it actually works. All right. In the circuit below, you're given blah, 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 and they already gave you the I, so once again, that plus that equals that. All righty. So what's your equation for the loop 1? Okay. Well, oh, hey, we're throwing numbers in. Isn't that fun? So here we got our plus 20. Now here we're going in this direction. It's the same direction that the current's going. This is going to be the opposite direction, though, according to the direction they gave us. I don't know that I would choose that as my direction, but that's what the author did. So 20. This is a drop in energy. This is the 5 ohms. So I1 in this case has been labeled I1 times your 5, and it's a drop. And the reason this is a plus here is because it's a minus. It's going against the current here. If it was me, I would have made it a minus, but I would have made the current go this direction for I2. But that's not what the author did. Okay, loop 2. Alrighty, so loop 2 got my plus 20. Still got my minus 5 there. Now the author chose this direction to be the I3. So as choosing that direction, this is also going to be a drop in 10 I3. And then because we're going opposite through a battery, we're going to oppose the motion. It's going to drop into. Okay? So we've got our 2 equations. Now we need a third one, and that's the junction rule. And according to this, I1 plus I2, the author drew this to be equal to I3. Or I3 equals 1 plus 2. Same thing. Okay? So now just define what the I's are, just math. We have 3 unknowns, but 3 equations. We're just going to start solving for them, substituting in one for the other. Okay? So substitute equation 3 for equation number 2. So since you have a 3 right there, all you do is you put in an I1 plus an I2 right for that one, and now you got it down to just 2 unknowns. Okay, so there it is. We substituted the I1 and the I2 for that 3, and now we're going to simplify that into a this. Okay? All right, now we're going to do this. You've probably guessed we could do the same thing again now here. We could substitute in for that. We could solve for an I1 right here, divide out by the 15 and everything, and put that whole equation in for that, which has the 2 in it. And now we have left 1 unknown in this thing. And now with our 1 unknown, you solve for the I there. You put it back into this equation that we did just right over here to solve for the second one. Then you put it back in this equation, you solve for the third one. But wait, slightly easier way to do all of this stuff with substituting. Okay, so now, so back to we have 2 equations, 2 unknowns. All right, continue on the next slide. Alrighty, so these are the 2 unknown equations now. Okay, so there's the 1 and 2. That's the very first one we did. I think, or is that the second one? It's one of them. So those 2 equations right there that we're looking at, just rearranging them. Okay. So we have 2 equations, 2 unknowns. The actual easy thing to do here is to just add your equations. You could substitute. You could solve for this like I talked about, divide up by the 5, so that's a 2I2, and that is a 4. And you substitute that whole, and you add it to the other side, and you add that into there. Now you have 1 unknown, and you solve away. But it's actually a lot faster just to add those 2 things together. 15 and 5 is a 20. Those drop out, and that's 38. Solve for the I. 38 divided by 20 is 1.9. Bam! So now we know the current going through the I1 section. Now if you plug that into that equation right there, what I1 is, and then you solve for I2 as you put in 1.9 in for that, Dios mío, you get a 1.05 amps, a negative. That just means your 2's backwards. Like I said earlier, weird that the author put that backwards, but They just wanted you to notice that that's what happens if you choose the wrong direction. It's not a big deal. The math still works great. Okay? Just going the opposite direction of what the author chose. Then you use the junction rule. We put that into that, blah, blah, blah.